Okay, dear students, now today we are going to learn the concepts of linear dependence. In the previous lectures, we learned how to find out the vectors are linearly independent. Now suppose here x1, x2, x3, dot xn vectors are there. Then their linear combinations with the scalars lambda 1, lambda 2, lambda n. The linear combinations lambda 1 x1 plus lambda 2 x2 plus lambda n xn equal to 0. By solving this one, we get equation like this: ax equal to 0 matrix form. This is homogeneous system of linear equations. Now, when it is homogeneous system of linear equations, then we have to keep in mind system is always consistent. System is always consistent. Therefore, rank of matrix A is equal to number of lambdas. Here, lambdas. Number of lambdas means nothing but unknowns. Lambdas here unknown. Lambdas are unknown. Then vectors are linearly independent vectors. Vectors are linearly independent. Now, today's point is if rank of matrix A is equal to R, which is less than equal to number of lambdas, then you say that the given vectors are linearly dependent vectors. Linearly dependent vectors means you get infinite solution for the lambdas. Then only you can say that is vectors are linearly dependent. We see some examples how to check the linear dependence and how to find out their relation between their vectors. You can consider one example. Say x1 is given vector which is 1, minus 1, 1. Second vector 2, 1, 1. And third vector x3 3, 0, 2. These are three vectors given to you, and these three vectors we have to identify either they are linearly dependent or independent. Now for this, assume that lambda 1, lambda 2, lambda 3 are three scalars. And their linear combinations with lambda 1 x1, lambda 2 x2 plus lambda 3 x3 is equal to 0. And this linear combinations equal to 0. If all the lambdas are 0, then vectors are linearly independent. Okay. And at least one lambda is not equal to 0 or infinite solution, then system is containing infinite solution. That time you say that given vectors are linearly dependent vectors. Okay. At least one lambda must be non-zero. Okay. Then we consider this system can be written into some matrix form. This given vectors. Here write in the column form 1, minus 1, 1, 2, 1, 1, 3, 0, 2. This is a three vectors, and we have three unknowns here. Say lambda 1, lambda 2, lambda 3, and equal to 0, 0, 0. These are homogeneous system system of linear equations. Okay, now we'll go for next slide. Now these homogeneous system of linear equations, now we can write in argument matrix form. A0 matrix form. A0 matrix form. Now A0 matrix means you get 1 minus 1 1 2 1 1 3 0 2, and here you get 0 0 0. This is called as argument matrix. By using row operations R2 plus R1, our job is here to make these entries 0. These entries must be 0. For that we are going to use these operations. And again, next operation to make this 0, R3 minus R1. Then we get here first row as it is, no change in the first row. Second row, add first row in second, means minus 1 plus 1, 0. Okay. Now adding this 2, we get 3. Adding this, we get 3. We get here 0. Similarly, first and last, subtracting. First row, subtract from third. 1 minus 1, 0. 1 minus 2. 1 minus 2, minus 1. 2 minus 3, again minus 1, equal to 0. 2 minus 3, 1 minus 2, like that. Now we get here, now if you divide 1, 2, 3, 0, if you divide row 2 by 3, row 2 by 3, you get like this. Here I'll write here, this is augmentation. Augmented matrix here. These are equivalent matrices. Now next job is here, make this to 0. Therefore R3 plus R2 to get matrix 1, 2, 3, 0, 0, 1, 1, 0. This is 0. This is also 0. This also get 0. Also get 0. Now this shows that rank of a matrix. Here you get rank of a matrix A is equal to 2, and which is less than number of unknowns. These are lambdas are 3. Lambdas are 3. Therefore, then we get infinite solution. Infinite solution for the system. Infinite solution for the system. Now, how to obtain? Let us assume that one variable out of these 3, z equal to t. Z equal to t. We got this matrix. Matrix. So write here matrix in the form of variable 1, 2, 3, 0, 1, 1, 0, 0, 0 into our lambdas. Lambdas are variable now. Lambda 1, lambda 2, lambda 3 equal to 0, 0, 0. As we already assumed that z equal to t. Now, by backward method, this row with this variable matrix. That's right. Lambda 2 plus lambda 3 equal to 0. Means this row with variable matrix equal to this coefficient, that is 0. Therefore, lambda 2 equal to minus t. Put lambda 3 equal to, sorry, you will assume here lambda 3. Lambda 3 equal to t, then lambda equal to lambda 2 equal to minus t. You get second value. Now for the first row, this is a row, first row with column variables. Lambda 1 plus 2 times lambda 2 plus 3 times lambda 3 equal to 0. Plus 3 times lambda 2 equal to 0. You get here lambda 1 value here. Lambda 2 is minus t, means minus 2t, plus lambda 3 is plus t equal to 0. Therefore, lambda 1 minus plus t equal to 0. Therefore, lambda 1 equal to minus t. This you get. Means when you get system is infinite solution, system has infinite solution, then vectors are linearly dependent. Therefore, given vectors are linearly dependent. They are linearly dependent, and they ask you relation between them. Now we have the equation here: lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 equal to 0. Now here put lambda values in this equation. Lambda 1 is minus t into x1. Lambda 2 also minus t into x2. Lambda 3 is t into x3 equal to 0. T is a parameter. You can divide throughout by t. You get x1 plus x2 equal to x3. This is a relation between all the three vectors. These are linear dependent vectors and their relation between them. Now here is an important trick either how to check this relation you got which is correct or not. Now here the given x1 vector is given to us 1 minus 1 1. A very important here concept, you can just observe it, check it. Then x2 vector is given to you, that is 2 1 2 1 1 2 1 1, and x3 equal to given to you 3 0 2 vectors. Now check is it our answer is correct or not. Just from the given vectors you can see here x1 plus x2 is this plus this is must equal to 3. This here 1 plus 2 equal to 3. You can observe it. You can see here. This is here. This 1 plus 3 1 plus 2 equal to 3. This here is first number. Same minus 1 plus 1 0. You get here 0. The next this element and this element plus 1 plus 1 2. Then you get here 2. Therefore, this relation is correct. Means x1 vectors, x2 vectors, addition must be equal to x3 vectors. Now component wise, you can check component wise. 1 plus 2 component, you get third component. But exactly correct. Minus 1 plus 1, 0, you got here 0. 1 plus 1, 2, you got here 2. This is a simple trick to check whether our vectors, our relations are got correct or not. Put the component values into relations, you get answer. Okay. Understood? We will go for the next example. One more example you can see. We'll go for the second example. Example number 2. We'll see 4 component vectors. X1 equal to 1 1 1 3. The next x2 vector equal to 1 2 3 4. Vector x3 component 4 component are there. 2, 2, 3, 4, 7. 2, 3, 4, 7. Now, without solving, how to check are they related or not related? This is very important simple trick that you can just observe it. Here 1, 1, here 2. Here 1, 2, here 3. You can see this component, and just observe the first component of all vectors. If you add these two, you get this one. Means if you add x1 plus x2, you get x3 component. Let's check it. Same 1 plus 2, 1 plus 2, 3. Here you got here 3 answer. 1 plus 3, 4. Here you got 4 answer here. 3 plus 4, 7. You got here 7. Means without calculation also you can identify given vectors are dependent and their relation is given to you like this. They are dependent and their relation is given to like this. Just you have to observe all the first component. After the first component, not only stick with one component, you can go for the any of the component which are given in the equations. And if they are satisfying the relations, then you can go for the that. Now, how to solve a step by matrix method? By matrix method. Now, given system can be written as, and again, can assume that lambda 1, lambda 2, lambda 3. There are three vectors that take three scalars. Three scalars. Their linear combination is x1 into lambda 1, x2 into lambda 2, and lambda 3 into x3 equal to 0. Now you can write directly a matrix equation into vertical form. Here 1, 1, 1, 3. x1 vectors, all the component must be written into vertical column form. x2 vectors. And here 1, here 2, here 3, here 4. And here 2, 3, 4, 7. This is our matrix, coefficient matrix. And here variables, here x, we don't take x1, x2, x3, x3, they are vectors now. Now we want variables. Our variables are lambda 1, lambda 2, lambda 3. These are the variables. Now these variables equal to, this is homogeneous system of linear equations containing three variables. Now again same the procedure, make the entry below the first leading element must be 0. This is leading element, below that we have to make 0. This has to make 0. This has to make 0 by elementary transformations. And I'll write here transformation R2 minus R1 at first entry 0. And R3 minus R1 we get second element 0. Then R4 minus 3 times R1 we get fourth component is 0. By using these operations, you get a relation or matrix like that 1, 1, 2, 0, argument matrix form. 1 minus 1 you get 0. Again, same subtracting. 2 minus 1 you get 1. 3 minus 2 you get 1. Argument matrix 0. The next 3 minus 3 times 1 minus 1 second row with third row with first row. 1 minus 1 0. 3 minus 1 2. 4 minus 2 again 2. This is 0. Okay, 3 minus 3 this you get 0. Again here 1 minus 3 times means again 1. Here 3 times 6 6. 7 minus 1 1 is again 0. Now you can see here. You can see here second row, third row, fourth row, all are looks like same. All are looks like same. To make them zeros, means you can make R3 minus 2 times R2, R4 minus R2. These are the next operations. After that, we get here matrix 1, 2, 1, 2, 0, then 0, 1, 1, 0. All entries you get 0, 0. All you get 0, 0. Now, this shows that rank of matrix K equal to 2. Here, these are two rows which are non-zero rows. There are two rows which are non-zero. The rank of matrix is equal to 2. Then this is less than equal to number of unknowns. Unknowns are here 3. Unknowns are 3. Again, this shows that given vectors are linearly dependent. Why? We have infinite solution. Infinite solution. So, then how to find out these linearly independent vectors relations? Now, this matrix system write into the shortest way. 1, 1, 2, 0, 1, 1, 0, 0, 0. You take only 3 rows, we required all remaining are 0. Now here you take lambda 1, lambda 2, lambda 3 equal to 0, 0, 0. As we got system as infinite solution, then assume that, let us assume that lambda 3 equal to t. Lambda 3 equal to t. Once you get lambda 3 equal to 0, or lambda 3 equal to t, then remaining by this second equation. By second equation is like this here. This equation with variables lambda 2 plus lambda 3 is equal to 0. Therefore, now you get lambda 2 equal to minus t by putting lambda 3 equal to t. Now for the first equation, go for the first equation. First equation here 1, 1, 2 with lambdas means lambda 1 plus lambda 2 plus 2 times lambda 3 equal to 0. Equal to 0. Then put all lambda values here. Put all the lambda values. We get lambda 1, lambda 2 is minus t, lambda 3 is plus t, then you get lambda 1 equal to minus t again. Lambda 1 equal to minus t. We'll shift to next one. Then here lambda 1 x1, lambda 2 x2 plus lambda 3 x3 equal to 0. Now see what are the values of lambda now here? Lambda 3 is t, lambda 2 is minus t, lambda 1 is also minus t. We go for the here means minus t plus minus t into x1 plus again minus t into x2 plus t into x3 equal to 0. Therefore, minus x1 minus x2 plus x3 equal to 0. Then this shows that x3 equal to x1 plus x2. Like that, you have to find out relations between them. Now, similarly, we'll check some examples without solving the concepts. How to find out without solving also to check whether the given vectors are linearly dependent or independent. We'll take some examples, other examples to check whether this Suppose one x1 vector is a x1 vector I'll take here 3 1 minus 4 x2 vector 2 2 minus 3 and x3 vector 0 minus 4 and 1 0 minus 4 and 1. Now observe it clearly. Here 3 plus 2, here no relation between characterizations. If you multiply something you can check it. Here 1 plus 2 3, here it's 4 minus 4 minus 3 minus 7, here no relations. If you multiply something and add it to the equations, we check. Now here 3 is the largest number. If you multiply across to each other, check it what you get. You multiply this equation by 2, this equation by 3, then you get 6, here 6 and 0. Now here this is 2, this is 6 minus, means we get some relations. Okay, we get some relations. Okay, means this 2 times this one, 3 times this, and this one x3. Means you get equation like this here. 2 times x1 must be added 3 times x2 plus x3 times. Check it here, just last entry, last point or component, minus 2 into this you get minus 8, 3 3s are 9, minus 9, and here 1 plus 1. So added this one, minus 8 equal to minus 8. Hence this relation satisfies both components. Like that, you can trial error method also. You can check how to verify given vectors are dependent or linearly independent. Okay, sometimes directly you can get, sometimes you multiply some scalar to the other vectors, then you get the component wise vectors. Okay, now you understood how to find out relation between linearly dependent vectors. Okay, today we'll stop here only.